Hello students, welcome to the 6th lecture, Real Gases or van der Waals gases. In this lecture, we consider the properties of real gases and how and why they differ from the prediction of ideal gas law. Real gases approach ideal behavior more closely at higher temperature and low pressure. But under high pressure and low temperature, they behave differently. Why this happens? The Dutch physicist Johannes van der Waals modified the ideal gas law to describe the behavior of real gases, so-called van der Waals equation of state. By this, the real gases are also called van der Waals gases. He includes the effect of molecular size and the interaction between molecules. For ideal gases, both effects are nil. First, I am explaining the effect of molecular size. Because the molecules of ideal gases are assumed to have zero volume, the volume available to them to move is always same as the volume of the container. This is particularly at low pressures. But for real gases, they have a measurable volume. At low pressures, this will not have much effect because the molecules are far apart and their size becomes negligible compared to volume. But as the pressure increases, the molecules come closer. As a result, the volume occupied by the molecules becomes significant compared with the volume of the container. Thus, the new volume available to the gases will be less than the ideal volume. Hence, the volume correction is that the actual volume to move freely is less because of particle size. If there are more molecules, there were more effect because if there are more molecules, the effect will be more, so that it will be pronounced at high pressure. Thus, the corrected volume V prime will be the ideal volume minus NB, where N is the number of moles of gas having a definite size, and B is called the van der Waals constant, which differs for each gas. Next is the pressure correction. The ideal gases are considered to have no intermolecular force of attraction. Particularly at low pressure, the molecules are far apart, and this concept may be correct at that time. But when pressure increases, the molecules come closer. As a result, the intermolecular force of attraction increases. Then the pressure exerted by the gas on the wall of the container will be less due to its relatively small strength of collision with the container. Hence, the pressure on the wall of the container will be less. Hence, at low pressure, the actual pressure will be equal to ideal, but at high pressures, we have to add a term with the ideal pressure to make both correct. That is, the pressure correction is that because the molecules are attracted to each other, the pressure on the container will be less than ideal. As the pressure depends on the number of molecules per liter, it is proportional to N by V. Also, since two molecules interact, the effect must be squared. That by we will get N square by V square, and it is multiplied by a proportionality factor called A, which is known as van der Waals constant. Thus, the observed pressure will be ideal pressure plus A into N square by V square. Hence, the van der Waals equation of state becomes: for n moles of ideal gas, it was PV equal to nRT, but n moles of a real gas or van der Waals gas, the equation becomes P plus A into N square by V square into V minus NB equal to nRT. Here, A into N square by V square term is the pressure correction factor for intermolecular forces, and the NB is the volume correction factor for molecular size. Here, P is the pressure of the gas, N is the number of moles of the gaseous system, V is the volume, R is the universal gas constant, T is the temperature, and A and B are the van der Waals constants characteristic of the gas. If we are taking 1 mole, that is N is equal to 1, the equation becomes P plus A by V square into V minus B equal to RT. So, students, study the equations well for both n moles of the system and 1 moles. By this, I am concluding the lecture about real gases, and I wish to summarize that no real gases exhibits ideal gas behavior, although many real gases approximate it over a range of conditions. Thank you very much, students.